Now next I'd like to generalize the nets that I've considered so far, and the way that I'm going to extend the definition from the previous slide reflects a observation that might already have been made for our examples. If we look at the train examples, we come to recognize that usually we can distinguish the different trains, and at least it's possible to count the number of trains. There could be several trains at Paris, and there could be several trains at Brussels, etc. Being able to distinguish between the different trains will be the third extension that I'm going to make. For the time being, we just consider nets for which it's possible to have a number of tokens on each of the places. This extension is called place transition nets. Place transition nets formally can be introduced as follows. Formally, a place transition net is a six-tuple where the first element in the tuple is called places, and the places correspond to what we so far called conditions. And then the second element is the set of transitions. These transitions correspond to what so far we called events. And then we have the flow relation just like before. In addition, we have the so-called capacity. Since we now are considering a number of tokens on each of the places, we are in general interested in defining a so-called maximum capacity for the places. Furthermore, whenever such a transition will take place, a certain number of tokens might be involved. We might remove a number of tokens from the precondition set, and we might generate a number of tokens in the postcondition set. And this number is defined by this fifth element of the tuple. And finally, we have the initial marking. The initial marking tells us how many tokens we have initially on each of the places. So frankly, the initial marking could already be included in another definition of the term condition event net. We could also define condition event nets in such a way that the initial marking is a part of the definition as well. So for these elements of the tuple, we have the following requirement. The first three elements are forming a net with places and transitions. The fourth element is a mapping from places to numbers, and these are natural numbers where initially we include the zero, add one special symbol to denote infinity, and then remove the zero again. This capacity is the maximum number of tokens that we can have on any of the places. Now this rather complicated dealing with the zero aims at making really sure that you understand that we remove the zero there. Having a place that has a capacity of zero does not make too much sense, because we could leave that out of our model right away. Then we have the fifth element of the tuple, which is the weight. The weight is a function from the different edges onto the numbers, and in this case we do again exclude the zero there because these numbers will tell us how many tokens we are consuming, how many tokens we are generating, and edges for which we are not consuming or generating tokens can be left out right away at the beginning. And the last element is the initial marking. The initial marking is a mapping from the places to natural numbers. And again, we extend this set on the right-hand side by one special symbol denoting infinity. So we can have an infinite number of tokens on a particular place. And in this case, we do include the zero because it can obviously easily happen that there is initially no token for a particular place. Now with this extension, the following can happen. Let's assume that we have a situation in which we have a certain number of tokens on the conditions in the precondition set. So we have 3, 3, and 3. And let's assume furthermore that we have certain weights on the edges, and we have also certain weights on the edges to the post-condition set. Now, if this transition Tj would actually fire, it would remove a number of tokens, and the number being defined by the weight on the edge. So in this case, there would be 1 token be removed, there will be 3 tokens removed, and there will be 2 tokens removed, and there will be 2 tokens generated and 1 token generated. So we see this change in the number of tokens on the right-hand side. In certain cases, we might want to avoid having too many symbols there in our graphical representation. So therefore, we are typically agreeing on certain defaults. If we are not explicitly specifying a maximum capacity, then the capacity is assumed to be unlimited. And if we are not specifying any weight for these edges, then we assume that just a single token is removed or generated. So the way in which these tokens are changing whenever a transition takes place is shown in detail in this slide. On this slide, you see how we can compute the total number of tokens, which is resulting from a particular transition T to fire or to take place. So the new marking M prime for each of the places can be computed from the old marking as follows. If we have a place which is in the precondition set, then the weight on the incoming edge will tell us how many tokens we are removing. If we have a place which is in the post-condition set, but not in the pre-condition set, then the weight on the edge will tell us how many tokens we have to add. And if actually we have a loop, which means that in this case we are not restricted to pure nets, if indeed we have a loop, then the difference will tell us by how many tokens this transition will change the marking on that place P. If a particular place is not at all connected to one of the transitions, then the number of tokens will not change if transition T takes place. So as an example, we see the change down here. We see down here how such a transition Tj will change the number of tokens. Now next I'd like to describe something which implicitly more or less we have already assumed during the explanation so far. I'd like to describe what is the required condition for some transition to take place. Some transition can take place if it's so-called activated, and a transition is activated if in the precondition set there are enough tokens, and if for the post-condition set there is enough capacity. So formally this can be written as follows. For all the places in the precondition set, the number of tokens must at least be equal to the weight of the connecting edge. And for all the places in the post-condition set, there must be enough capacity left on these places. So if we increase the number of tokens by the weight on the edge, we should not exceed the maximum capacity of the post-condition set. If such a transition is activated, it can take place, or we can also say such a transition can fire, but an activated transition does not have to take place or does not have to fire. There can be other transitions in our Petri net model that could also fire, and we are never really sure in which sequence some transitions will fire. So if there are several transitions that are activated, we will have to select non-deterministically which transition will actually fire. And if if we have to consider all the possible sequences of transitions, we will have to consider all the possible options for resolving that non-deterministic part of the model. In the context of Petri nets, we never talk about time, so we never talk about how long it takes until a certain transition takes place. We are intentionally trying to keep the notion of time away from Petri nets because we would like to focus just on causal dependencies. Now, on the previous slide, we have just seen how the number of tokens on the places is affected by a certain transition taking place. And on this slide, I'm now trying to introduce a shorthand for this change. We saw on slide 14 that m prime can be computed from m using this equation. And next, I'm going to introduce a shorthand for what we need very, very frequently in this definition of the number of token changes. We introduce a vector t underscore, which is associated with a certain transition. And this vector t underscore defines for each component p by how much the firing of this transition will change the number of tokens on place p. So that means if that place is in the precondition set but not in the postcondition set, the weight on the incoming edge will define the decrease in the number of tokens. If that place is in the postcondition set but not in the precondition set, the weight will define by how much we increase the number of tokens. And if that place is a part of a loop, then the difference between incoming and outgoing edge weights will tell us by how much we have to change the number of tokens. Obviously, if there is no edge involved, then the number of tokens will not change. Now, with this notation, there is a much shorter way of defining how the new marking can be computed from the old marking. We can write as follows: for every place p in our place set, the new marking can be derived from the old marking by just adding the corresponding element of vector t underscore. Now, in this context, this operator plus is a scalar operator, and we can come to a even shorter way of specifying this computation by using matrix notation. If we use matrix notation, we can write as follows. We can write m prime equals m plus t underscore, where now plus denotes vector add, so that means it runs over all the elements in our set capital P. So this is how we can denote the changes in the number of tokens. Now, from these vectors t underscore, we can form a matrix which is then not just describing the impact of a single transition, but it will then be describing the impact of all transitions. So what we are doing right now is we are using these vectors t underscore as rows in a matrix which we call n underscore. And now I'm moving to the next slide to demonstrate using that example how this vector or how this matrix n underscore looks like. We see that in this matrix n underscore, we have the different vectors t underscore as the different columns. And we see that the different entries here describe how a particular transition will change the number of tokens. For example, if transition T1 takes place, then for place 1, we will have 1 additional token. For this place 2, which is that one, we will have a decrease by 1. And for this place 9, we also have a decrease by 1. And for place 13, we will have an increase by 1. So in this way, this matrix is describing how the number of tokens is changing whenever a particular transition is firing. So let us now switch back to this previous slide. From the example, I think it's obvious to see that indeed this matrix n underscore is providing a mapping from p times t to integers. These integers may actually be negative, and if they are negative, then this means the number of tokens is decreasing. And we see down here that we are using these vectors t underscore as the columns in this matrix. Now, just to be sure that you really understood the key purpose of this matrix, component t in row p indicates the change of the marking if to the place p if transition t takes place. Now there is one final remark for this matrix at the bottom of the slide. For pure nets, this matrix n underscore in combination with m0 is a complete representation of a net. So obviously, if we do have poor nets, then all the properties of our model are captured in this matrix n underscore, if we also know the initial number of tokens. There may be the question, why do we require these nets to be pure? Well, if these nets are not pure, then we have loops, and for the loops we will enter into this matrix n underscore only the difference between the weights of the incoming and the outgoing edges. And obviously, if we just know the difference between the two weights, we cannot really compute the original numbers from the difference. And therefore, if we have impure nets, then in general the description by matrix n underscore and m0 is not sufficient to really represent the entire net. Okay, next I'd like to describe one particular way of using such Petri nets models. I'm looking at so-called place invariants. These play invariants provide us with a very much standardized way of proving certain properties of our net models. These place invariants are also reflecting the situation that very frequently people ask, well, do tokens remain constant, or can they increase, or can they decrease? It turns out that looking at this question actually provides us with a standardized way of proving properties of Petri net models. So for this purpose, we are initially looking at a particular transition Tj. And for such a particular transition Tj, we are trying to find subsets R of the overall set P, such that the accumulated weight or the accumulated number of tokens for that subset R remains constant. That means if we sum up over all the different places in this subset R, we would like to have no overall change in the number of tokens. As an example, please just look at the bottom of the slide. There you see that if this transition Tj takes place, then we will consume 3 tokens, but we will also generate 3 tokens, and therefore the overall number of tokens has not changed. Now what we're trying to do over here is we are trying to find such subsets R such that for this set the number of tokens is not changing. Now it's somewhat inconvenient to have the sum to run over just over certain elements of our overall set P. It runs over just a subset. In many cases, we would like to use matrix addition, matrix multiplication to work with these vectors, and that is a little difficult if we have to use these subsets. So we can work with matrix addition and with multiplication based on an entire vectors if we introduce a so-called characteristic vector. A characteristic vector is linked to a particular subset R, and it has components for each of the places. Now, for a particular place P, the value of this characteristic vector will be 1 if a place is included in the subset R, and it will be 0 if that place will not be included in the subset R. Now, with this introduction of the characteristic vector, we can rephrase our equation as follows. Let's initially start with this summation just over these elements in the set R. We can replace this sum by a sum which now runs over all the different places. If we take advantage of this characteristic vector, which will just filter out all those elements over which we don't want to sum up the different contributions from these vectors t underscore. So in this way, we can sum up over all the different places in this set P. And we don't need to select a certain subset of index values over there. Now, if we carefully look at the sum, and if we think about our education in linear algebra, we come to the conclusion that this is nothing but the scalar product of the two vectors t underscore j, more precisely, and cr. So we can use the scalar product in order to find such subsets of P for which the overall number of tokens is constant. So on the next slide, I put down just a copy of the last equation from the previous slide. So we see that in order to find such subsets R, we need to look at scalar products. However, what we considered so far just reflects a situation where the total number of tokens remains constant for a particular Tj. In general, however, we are interested in subsets of the set of places such that for all transitions we will not be changing the total number of tokens. Now, if we are interested in such subsets R, we have to consider all the different tokens, and this is what I did at this part of the slide. We see that we are now requiring this scalar product to be 0 for all the different transitions that we have in our net model. Now, this means that we are now arriving at a set of equations, and it turns out that these are linear equations where these characteristic vectors are the unknowns. Now, there is a shorthand for this set of linear equations, the shorthand being written down there. The shorthand is that the transposed vector, that the transposed matrix n underscore times the characteristic vector should be equal to a vector of zeros. Just to convince you that this is indeed true, I'd like to look at what this matrix notation actually means. Matrix notation means that we take that entry there from the matrix, multiply this by the first entry from this vector, take the second entry there, multiply this by the second entry from that vector, and repeat this until finally we are multiplying this last entry there in this matrix by the last entry there in this vector. And we will then do a similar thing for the second row in this matrix n, or more precisely in the transposed matrix n underscore. So this means that this notation is actually the same as the one that we are using over here. So this is just a somewhat different formulation of the same equation. So that means that now we have arrived at a system of linear equations, and our goal is to solve that system of linear equations. This matrix n does reflect the structure of our model, This vector reflects the unknowns. This reflects information about invariants that exist for our model. Now, obviously, this is a linear and more precisely a homogeneous linear equation. And you might be familiar, hopefully you are familiar with techniques for solving such linear homogeneous equations. However, there is one additional constraint that we have to take into account when we look at this system of linear equations. These characteristic vectors must contain only ones and zeros, and that's a really tight constraint. That's a constraint that's usually not considered when we look at sets of linear equations. Now, in general, if we have equations with multiple unknowns that must be integers, such equations are called diophantic equations, and the name is derived from the Greek mathematician Diophantos, who lived about 300 years before Christ. And he was looking at such equations where the unknowns must be integers. Now, it turns out that diophantic linear equation systems are much more complex than the standard linear equation systems. Actually, one could prove, we are not doing this over here, that solving such diophantic linear equations is NP-hard, which means that the runtime will typically increase exponentially with the size of these models. Now, for solving these linear equation systems, we might be using different techniques. We might think of using a certain mathematical programming package. However, we can also try to do this manually if the particular example is not too complex. Now, therefore, let's look at our particular example, where we have modeled the system of high-speed trains. In our particular example, we have a matrix n underscore that can be transposed. So on this slide, you see the transposed matrix n underscore. Now we would like to solve that linear homogeneous equation system. At this time, it's very useful to think about what we remember from our course on linear algebra. From the course on linear algebra, we should remember that sometimes it is very useful to consider dependencies between rows because they actually have an impact on the dimension of the solution space. If you look at this particular matrix, we see that the sum of all the rows is equal to 0. If we look over here, for example, we see the sum is equal to 0, sum is equal to 0, sum equal to 0. So overall, we see that for all the columns, the sum is equal to 0. So also up here, sum is equal to 0, and this applies to all the different columns there. That means we have one linear dependency. And when we are trying to solve that equation, we can delete one of the rows because there the values are just resulting from the other values. And in many cases, it will, for example, be very convenient to delete that one row, which is not really having most of its value very close to the diagonal. So because of this linear dependency, the overall rank of this matrix is not equal to the number of rows that we have, but equal to the number of rows minus this one linear dependency, which means that the rank of this matrix is 9. Now, also from the course on linear algebra, you could possibly remember, hopefully remember, that there is a dimension of the solution space which is equal to the number of columns that we are having over here, which means it's 13, minus the rank being 9. As a result, we see that the dimension of the solution space is 4. So that means we have to work with a 4-dimensional solution space. At this time, I'd like to look at how we can possibly come up with information about that 4-dimensional solution space. We can think of trying some mathematical programming package, but sometimes it's actually more fun to do an exercise and try to get these solutions also manually. In this case, it's indeed possible to get these solutions manually because we have so few entries in this matrix and most of them are arranged along the diagonal. As a result, it turns out that we can actually solve this linear equation system manually. Now, if we want to solve this linear equation system manually, this means that we are looking for information about that four-dimensional solution space. And if we would like to get information about the four-dimensional solution space, it does, of course, make sense to try to find four basis vectors for that four-dimensional solution space. Now, a very easy way of finding four basis vectors for the four-dimensional solution space is to select four components, and then for the four components generate four different basis vectors, and for each of the basis vectors we would set one component to 1 and all the others to 0. So in this way we are reasonably sure that they can actually serve as independent basis vectors. So the question only then remains which of the components would we select for this purpose. Now, for this purpose, we have to look very carefully at this matrix. The first thing that we see is the fact that we can select the entries there for row 7, 8, and 12 rather easily. Because what could we do there if we would select the entries there for 7, for example, for 7? In order to remove as many dependencies as possible, I'd like to remove the very first row there. In this way, we don't have to care about that one. And then when we try to iteratively find the corresponding values for the other components of that basis vector, we have to look at dependencies as they exist in this matrix. And we see over here that we have certain dependencies that exist, and we would iteratively then compute the different elements there. And we can see if there is some other dependency that we should consider. We see over here that there is something that we consider over here. But essentially, these different elements are independent, and therefore it's actually a good way to, a good decision to select any of the components 7, 8, or 12 to be included in this set of 4 components. The other thing that we can do is we can look at the net and actually exploit the fact that we know what we're modeling there. The other thing that we can do is we can, for example, assume that in our set of places we will be excluding this particular place, and then we can try to set other places to be not included in the set, and then try to compute from this matrix which other places could also be included in that set. And as a result of this consideration, I will do the calculation based on the assumption that for these 4 components we will be using component 6. Any of these 3, in this case I'm selecting 12. We are also selecting 11, and we are selecting 13. If we would select the wrong component there, then we would be getting to contradictions during the solving of our linear equation systems, and then we would have to consider others. So let's assume that we do these computations based on these 4 components. So the overall idea now is to initially set one of them to 1 and the others to 0, and then use this linear equation system to actually get information about the other components of the basis as well. So we start with these 4 elements as the initial 4 elements of our first basis vector, and then we look at the last row of our matrix over here. So for the last row of our matrix, we see that we have a 0 over here because that's a result of what we are setting up there. Then we have T10 of P13, which is a -1. We have a -1 there. Then we have B1 of P11, that is initially set to 0 as well. And then we have T10 of P11, so that's the entry that we have over here, so that's a 1. And we have T10 of P10, so that is, sorry, that was a -1, and that is a 1 over here. So if we look at this equation, we see that obviously this term over here, that's equal to 0, that term is equal to 0 as well. And for the overall sum to be equal to 0, it is necessary that this term is equal to 0 there as well. So this gives us one additional component of this basis vector. Now, for doing this for the first time might need getting used to it, but doing this for the second time now I think looks a lot easier. We are essentially repeating the same exercise. Now, when we repeat the same exercise, we are using the information that we have from the first calculation. T9 of P10, T9 of P10, that is the entry that we find over here, that is a -1. And then we have B1 of P9, that's the component that we would like to compute. And we have T9 of P9, that's the other entry that we have over there, and that is a 1. So it's obvious that the second term is equal to 0. For the overall sum to be equal to 0, it's therefore required that this component of the first basis vector is also equal to 0. So we have computed the next component of the first basis vector, and we can repeat this exercise for all the rows that we have over here in our example. I will not go through all these computations. I think you can believe me. You can also try to do the exercise at home. This is finally the result which comes out of this calculation. This result gives us a first basis vector. Now, in this case, we are actually extremely lucky. We are extremely lucky because we require to look at vectors in our four-dimensional solution space that contain only 1s and 0s. Now we are lucky because our first basis vector does only contain 1 and 0s. And that means that this very first basis vector can also serve as the first characteristic vector. Now let's look at our example and see what this really means for our example. If we look at which places are indicated by this characteristic vector, we see that these are exactly the places along this loop in our Petri net model. And these are the places that we are touching for the trains that go from Cologne to the Gare du Nord. So the meaning of having an invariant here, the meaning of having a constant number of tokens is that these trains from Cologne, they never get lost. And I think that's very good news for those people who are entering a train at Cologne. They are pretty sure that their train will never get lost. The total number of trains will remain constant. So that's pretty good information. So now let's repeat the exercise for the second basis vector. So in this case, again, we will try to set one component to 1 and the others to 0. So in this case, this component has been set to 0 and this component has been set to 1. And now we are looking at the last row again. If we look at the last row again, then we start with B2 of B13. So this is what we are setting to 0. Then we have T10 of P13. This is the last entry that we have over there, so that is a -1. Then we have a B2 of P11. That's the component that we're setting to 1, so we have a 1 there. And then we have a T10 of P11. That is the entry that we have over here. That is a -1. And we have B2 of P10. That's the unknown in this equation. And we have T10 of P10. That is this one that we have over here. So we see that this term is 0, this term is -1. Overall, the sum has to be equal to 0. In order for the sum to be equal to 0, this component has to be equal to 1. So therefore, we have found another component for the second basis, and we can repeat the same exercise. Again, we will find another component there for this basis, and if we repeat these computations for all the rows in the matrix, this is what we will be getting. Okay, so in this case we found a second basis vector, but unfortunately it's not a characteristic vector because there are -1s there. So our target is to find another characteristic vector. Now in this situation we can take advantage of some knowledge which hopefully exists due to the course on linear algebra. According to standard knowledge in linear algebra, we know that whenever we have such a solution space, the sum of two solutions will again be solutions. So this means that the question now is, what could we add to this basis vector in order to have a characteristic vector? Well, it's pretty easy if below this basis vector we are writing the first basis vector. We write the first basis vector below, and if we compare the different entries there, we come to the conclusion that the sum of these two basic vectors is providing us with another characteristic vector, with a vector that only has 1s and 0s. So again, we can look at our model and try to figure out what this really means for our model. If we try to identify the places corresponding to the ones here in our characteristic model, we come to the conclusion that these are the trains that are starting from Amsterdam and making their way to Brussels. So this means that we can be pretty sure, as passengers entering at Amsterdam as well, that none of the trains that we are driving actually gets lost. So that's good news for the railroad traffic as well. Now, I don't want to do the same exercise for the other two basis vectors as well. I think you can either believe me or try to do these computations at home. This would be the third basis vector, or also the third characteristic vector, and that's the fourth basis vector, which immediately would be a characteristic vector. We can try to identify the corresponding places there in our model, and we would find that the third characteristic vector corresponds to the train drivers. So that means that the train drivers that are starting from Amsterdam also don't get lost, and the fourth characteristic vector reflects the fact that these local trains at Paris also don't get lost. So that's also pretty good news for the people traveling on these trains. So in this way, we managed to prove properties about our model in a very much standardized way, and we don't have to invent new proof techniques for each and every model. So for this type of Petri net, for these predicate transition nets, we do have a good number of applications. These nets are very convenient for modeling resources. I think it's easy to imagine that the number of tokens could reflect, for example, the number of buffers that are available, the number of processors that are available, or some other hardware units that are available. Frequently, these models are also used to demonstrate that the attempt to guarantee mutual exclusion also is successful and is guaranteed for a particular model. And also from the context, it's already very clear that with predicate transition nets, we can also very easily model synchronization. That's what we did when we looked at these trains in our examples.